So when I'm talking about evaluating improper integrals, I'm actually going to talk about two types. This type 1 of improper integral is integrals that have infinite limits of integration. So if you're actually trying to integrate an integral over an infinite limit, like say let's suppose you're trying to integrate it from a to infinity, or from minus infinity to b, or even from minus infinity to infinity. Now, believe it or not, some of these integrals will actually converge to a value, but what you have to do is you have to do these with limits. So if you want to integrate, say, from a to infinity, then what you have to do is you have to replace infinity here with b, and then you have to evaluate the integral from a to b, and then you let b approach infinity. Okay, now, but if you integrate from negative infinity to b, then you put the negative infinity at the lower end and b at the upper end, and then you integrate as a goes to negative infinity. I mean, you take the limit of that integral from a to b as a goes to negative infinity. And if you're integrating from minus infinity to infinity, you actually have to pick a number between minus infinity and infinity, just any real number, and then integrate from minus infinity to c, and then from c to plus infinity. So let me show you one of each type here. So I'm going to do the first type first. Okay, so let's say I want to integrate from 1 to infinity natural log of x over x squared dx. Okay, now I don't want to get lost in the integration here, so I'm going to kind of smooth over that part. But if you want to integrate from 1 to infinity some function, then you're actually going to integrate from 1 to b, and then after you evaluate that integral, you're going to let b approach infinity and see what happens. So if you integrate natural log over x squared, and you can do this integration by parts if you want to go off to scratch paper and do it, and you'll get minus the natural log of x over x minus 1 over x from 1 to b. Now, if we evaluate this at b, we'll get minus the natural log of b over b minus 1 over b. And then if we evaluate it at 1, we'll get minus the natural log of 1 minus 1. And then so finally, since the natural log of 1 is 0, and we're doing a minus here for this minus 1, we're going to get plus 1. So we're going to get these two terms, and then we're going to get plus 1. Okay, now what we want to do is we want to take the limit of this as b approaches infinity. Okay, so let's take a look at right here. Here's where I'm going to do it. So if I take the limit of this as b approaches infinity, then I'm going to just do the limit of each term. So I'm going to take the limit of the first term minus the limit of the second term plus the limit of 1. Now, let me go ahead and tell you the second and third term. You know, if you have 1 over b as b goes to infinity, 1 over b goes to 0. And you know the limit of 1 as b goes to infinity is just going to be 1. So the second term, that's just going to be minus 0. The third term is going to be 1. Now, for this one, I actually just use L'Hopital's rule, because if b goes to infinity, you get infinity over infinity here. So L'Hopital's rule says you can take the log of the top over the log of the bottom. And, I mean the derivative of the top over the derivative of the bottom, and then take the limit. So now you can see that the derivative of natural log of b is 1 over b, and the derivative of b is 1. And so as b goes to infinity, this term goes to 0. So the first two terms actually go to 0, and then the third term goes to 1. So I get 0 minus 0 plus 1, which is actually 1. So this integral actually does have a limit, and that limit is 1. So it converges to 1. Okay, now the second case is where you're integrating from minus infinity up to a number here. And so here, I gave you a little hint here. If you actually evaluated this integral, you could evaluate it using the power rule, and you would get minus 2 times 1 minus x to the 1/2 power. So we'll use that in a minute. Okay, so how do we rewrite this? So instead of going minus infinity to 0, we'll actually go from a to 0, and then we'll let a go to negative infinity. So then I evaluate this integral, and I told you already I get minus 2 excuse me, times the square root of 1 minus x, because that's what that is. And then if you evaluate this at 0, if you evaluate this at 0, you're just going to get minus 2, because you get minus 2 times square root of 1, so you're just going to get minus 2. And if you evaluate this at a, you're going to get minus 2 times the square root of 1 minus a, which is this term. And now, if you take the limit of this, well, you're going to get negative 2 for this term. But if you take the limit of this, if you replace a with negative infinity, you're actually going to get 1 plus infinity in the square root. So basically, you're going to be taking the square root of infinity here, which is infinity, and then multiplying it by 2, and so you'll get still get infinity. So you get minus 2 plus infinity, which is infinity. So this interval actually diverges. Now, if you're integrating from minus infinity to infinity, then what we need to do is we need to find a number between minus infinity to infinity that we can use here. And so I'm just going to choose 0. So I'm going to break this integral up into two integrals. So instead of going from minus infinity to infinity, I'm going to say I'm going to integrate from minus infinity to 0 of this function, and then integrate from 0 to infinity of this function. Okay, so if I integrate from minus infinity to infinity of this function, then you might remember that 1 over 1 plus x squared integrates to arctan of x. So I'm going to replace the infinity with a and let a go to negative infinity. But now let's evaluate this integral. Well, it's going to be, when you integrate 1 over 1 plus x squared, you're going to get arctan of x. And then if you evaluate it at 0, you get arctan of 0. And then if you evaluate it a and apply the fundamental theorem of calculus, you're going to have minus arctan of a. Now, if you let a go to negative infinity, first of all, this arctan of 0 doesn't care. It's going to be 0. But if you let this go to infinity, well, the arctan function as a goes to negative infinity actually approaches minus pi over 2. So, if you graph the arctan function, you can see that the closer x gets to minus infinity, the closer this gets to minus pi over 2. So actually the limit of this is minus pi over 2 as a goes to negative infinity. So you're going to get 0 minus negative pi over 2, which is pi over 2. Okay, now what about the 0 to infinity? Well, the 0 to infinity, we have to replace that with the integral 0 to b, and then take the limit of that as b goes to infinity. Well, it's still going to integrate to arctan, so we're going to have arctan from 0 to b. So we're going to have arctan of b minus arctan of 0. Well, we know arctan of 0 is just 0, and the arctan function, if you look at the arctan function and let x approach infinity, you'll see that the arctan function actually has a horizontal asymptote, so it's going to approach pi over 2. So this, by letting b go to infinity, this is going to be pi over 2, and of course this is going to be 0, so you get pi over 2 minus 0, which is pi over 2. Well, then, as I said, the result of the integral from minus infinity to infinity would just be the sum of these two integrals, and now the sum of these two integrals is just pi over 2 plus pi over 2, so now your answer is pi. Okay, so that's how you deal with these limits that approach infinity. And in the next example, I'm going to show you the type 2 improper integrals that actually have infinite integrands.